The coldest place in the universe is the Boomerang Nebula in the Centaurus constellation. At minus 272 degrees Celsius, or 1 degree Kelvin, it is only a single degree above absolute zero. Here on Earth, scientists have been able to get even colder than that by using lasers to cool individual molecules of sodium and potassium to 500 nanokelvins, but even they couldn't get to absolute zero. The third law of thermodynamics defines what absolute zero is and ties together the concepts of entropy and temperature. It states that the entropy of a perfect crystal approaches zero at a temperature of absolute zero. So an important idea to note is that absolute zero may not be able to be achieved experimentally. This is because we know from the second law of thermodynamics that heat will spontaneously move from a warmer body to a cooler body. So the object that you're trying to cool to absolute zero will be taking in heat from its surroundings. Despite this, absolute zero is an important theoretical concept. So the lowest possible entropy can only occur in a perfect crystal, which is a structure where all of the atoms that form it are identical and positioned in perfectly symmetrical ways. Any imperfections in the crystal carry an energy, so the entropy won't be minimized. Equally, any residual thermal energy within the crystal will create thermal motion within it, and again, your entropy won't be at a minimum. Conversely, that means that if we can't get to absolute zero, then nothing in the universe is going to be completely still, as we'll always have some motion due to thermal energy. One of the earliest forays into low temperature research was made by James Dewar, who was the first person to be able to liquefy and then solidify hydrogen gas. This reached a then record low temperature of 13 degrees above absolute zero, at which point he postulated, "There or thereabouts, our progress is barred." Nearly a decade later, Prussian scientist Walther Nernst announced his heat theorem, which would later become known as the third law of thermodynamics. This can be exploited when storing and using gases. For example, carbon dioxide as a gas has a high entropy and a relatively high temperature. We can reduce both by solidifying CO2 into a snow-like consistency. By releasing the pressure, some of the liquid carbon dioxide vaporizes and causes a rapid temperature drop, and this extreme cold makes the substance solidify. I've made dry ice. Similarly to the zeroth law, the third law of thermodynamics may seem simple and obvious. However, it is the final piece of the puzzle which helps us to explain our world and the nature of its heat and energy.